Okay, thank you very much. I'd like to say, Robert just asked me how I pronounce my name, and I like to say Jerry as in mouse, Clough as in Brian, but you have to be a certain age to know the last one. I'm going to start with a question. How many people have ever mapped a max speed tag on a way? How many people have mapped a max traffic sign equals max speed on a node? And of the 3 or 4 people who did the latter, what is the ratio of the number of traffic signs you map to ways? Is it near to 1 or is it near to 100? Near to 1? Near to 100?
Depends what you include. Depends on where I map at.
Yeah, but this is an example of what I'm calling Schrodinger's data. It's a bit of a cheesy term, because all those max speed signs are implicit in OpenStreetMap, and we could, if we wanted to, write some code to derive them and place them in a data set. That's a very simple example. I chose the title because I came across this blog post by Giuseppe Salozzo, someone will you know is an open and data enthusiast in Britain. And he had a big data set of bus stops, an open data set of bus stops. But the open data set did not tell you which bus stops were in bus stations. It's a classic data problem. Every data set I've worked with in the last 35 years exemplifies this. There are things which are implicit in the data but are not actually represented. And you often have to spend a lot of time building systems making such data explicit. Simple examples, data not information. My dad, who's 93, recently had a blood test, and there were hundreds and hundreds of data points, but no piece of information saying, you're okay. You often get unknown knowns, so your data contains the information, but no one knows that it's somehow in that data. You get embedded data. The classic example I can think of is a company I worked with which had a lot of products for children which were branded with Disney names. So something Mickey Mouse. But there was nothing in the data except in the name of the product to find them. So we wrote this huge query matching every single Disney character we could think of to try and pull these specific products out of the database. And then there's a latter category, which is what I call emergent data. It's the relationship with data points themselves, which you can use to infer other data. And it's probably the latter category I'm most interested in, but it's not particularly useful, familiar term to people. So it's everywhere. And the reason it occurs, the data's not being used for its original purpose. The data is collected to support the common use cases. We also get fragmentation. We used to collect data at a certain level, and then we want more and more detail. And as a result of that, we lose the original aggregated view of the data, and it's not necessarily that easy to come back to. And very common across all organizations is failure to collect data. But from an OSM perspective, we've got a lot of other things applying. One of which I haven't got on this slide, which Martin mentioned, was that we have lines, not areas. That introduces various intrinsic things. We could be OSM's potentially a global geodatabase, but in practice it doesn't have semantic concepts just for example, LTNs, junctions, urban areas. But we've probably got enough information to pull some of those concepts out. I won't go through all those details. Obviously, we've got massive degree of patchiness. We've got patchiness in the types of contributors we have, their education levels, their gender, all sorts of things. All of those influence. So unlike, say, a so-called authoritative data set, OSM is going to be much less consistent, particularly across time and across areas, across location. When I started thinking about what I was going to say, I discussed this with Stefan Keller in Rapperswil, and he alarmed me a bit by realising the original scope was much larger than I'd thought about. And he provided typology of the implicit data in OpenStreetMap. And I'm really only going to talk about what he calls the Gestalt type. Things which, if you look at a map, you can perceive. If you look at an OSM map, you could probably quickly draw an outline around the urban area of Dundee, for instance. I'm also not going to talk about solving these problems by extending tagging models or relation models. I'm interested in what can we do with the data that's there. And enrichment from, and it's got to be internal to OSM. It's the internal logic of OSM, not applying external data sources. Similarly, the things which you can do with tags, just with tags, but I'm mainly interested in the geospatial, where there's pure geospatial contribution as well. And this is an attempt to synthesize various things I've done over a number of years, and I'm going to concentrate on my own examples, but I'm very aware that there are, if you scroll back through all the SOTMs that's been, there are lots of examples of people doing things of this kind. And Martin just provided two, I think. So for tag only, the sorts of things we want to do, we want to enrich the data. We might want to add hierarchies like Overture Maps did. I've done that with retail. We might do some simple enrichment with geocodes, for instance, attaching the local authority or the country to retail points of interest or something like that, so that you can do a more interesting analysis across countries or whatever. Or you might just want to harmonise all the different variants of the tagging scheme. And I've included, this is an example of what Andy Townsend does on the Someone Else Map Style Lua code, where he's combined all the different ways people map shops selling mobility aids so that you can get a single view. And there are plenty of tools for this. You can use Lua with various OSM to PGSQL and I think Osmium. If you're really mad, you can try and use Osmosis Tag Transform. You can do some quite nifty things for small data sets with Overpass, although one often comes unstuck with the syntax on there. And obviously you can extract the data and put it into your own flavour of favourite geospatial manipulation software, QGIS, PostGIS, GeoPandas, R, whatever. So I'm now going to talk on about the geospatial ones with the geospatial component. I'm really going to run through a limited number of examples. I'm not going to talk very much about the underlying things because each of these are quite complex. I'm started with something that I'm not very familiar with, but this was a bit of work by Dan Stowell, who some of you will know, who currently is a researcher at Naturalis and the University of Utrecht, identifying bird sounds. And this was one of his early, when he was, these Gaussian distributions were one of the things he started using, and he was playing with them. And the other word which is used for this comes from I believe it comes from the mining industry, kriging, where you have incomplete data across an area and you want to work out where you should go and look for more deposits. You can also do this with botanical sampling, where you've got, again, patchy, incomplete data, and you want to build up a bigger picture across a given geographical area. And Dan did it, this is the fun bit, he took all the nodes with elevation tags and tried to create an elevation model of Britain just from OSM nodes. And it sort of looks sensible. That's fun. And the technique could be applied for other things, but I've never got my head round quite how to do it. This is the sort of thing that I've been interested in. At some point I was looking at German retail, and I discovered that land use equals retail wasn't necessarily mapped in some German cities, so I thought, well, could I derive it? My first attempt is shown over here. This was about 2013, and a more recent attempt in the 30-day map challenge using a much more sophisticated approach. But that was a 5-minute map. So first of all, you find all the retail points of interest. In this case, I found them within grid cells 75 meters square. That's because of my influence of biological recording. Everything's done on grid cells, so it's and then I merged adjacent grid cells with points of interest, built up little patterns, and then put polygons, convex holes around them, because at the time PostGIS or QGIS wasn't very friendly about it. Broke when you tried to do the shrink wrap concave holes, and I repeated this in the whole thing in 5 minutes for the map challenge 2 years ago, because by then I'd discovered a wonderful technique called DB scan clustering, which basically does all the work in a single operation in QGIS or PostGIS. And at the moment, that's still my favorite technique for all sorts of things. It's a bit like I've got one tool, it's everything's a nail and this is my hammer, but this is the work of Stefan Keller's group, reported at State of the Map 18 in the academic channel, and you can go on his website and see his slides. I've just tried to summarize this. If you look on a Google map, you see nice little colored areas which are called areas of interest, and they're combining lots of data, including mobile phone signal and so on. And he wondered if he could reproduce that kind of thing in OpenStreetMap. And his approach was very much gathering POIs, except he used buildings. He clustered them, created concave holes, and then he did various fancy polygon tricks to simplify them, get them closer to the street network, etc., and created a data set for the whole of Switzerland. So you're beginning to see that there are given techniques which appear again and again in manipulating this kind of data. The one I've spent most time on over the years is urban areas. We have no concept of an urban area in OpenStreetMap. And I've tried a number of different techniques. One of the problems is the residential road in America, so you can't rely on residential roads to tell you that it's a rural area, an urban area. So the techniques I've used are looking at road density, again in cells. And this is the area around Pittsburgh in Pennsylvania. This one uses a much simpler technique. You just take all OSM line segments, which are highways of some kind, not service, not track, etc. And you take all of those which are less than 2 kilometers or 1 kilometer. You merge them together, either using a method of just connecting them up and building graphs, and then find out how many graphs you have and then wrap around the graph. But actually you can do it with DB scan clustering as well. And another technique, and this last picture is from this year's 30-day map challenge by someone in Germany, a Chilean guy in Germany, who used a technique where you use the road network and you turn that into polygons. And small polygons are probably in urban areas and large polygons aren't. The big problem with that technique is when you have dual carriageways, you get very small, long, thin polygons. And you have to do things like measure the ratio of the size of put an ellipse in the polygon and look at its ratio. So the this simple short streets work, which I discovered, but then discovered had been reported in 2014 in State of Map Argentina, works very well. And I built a vast worldwide data set, except for Japan. My algorithm failed in Japan. And I so put the work aside, and I looked at it again in the 30-day map challenge 2 years ago, and discovered why. I was able to just look at Japanese data. In Japan, rural roads go through loads of bridges, loads of tunnels, and they all have short line segments. So basically, my algorithm was trying to find a graph which was every road in Japan. I've tried one other approach, which is to take land use, certain classes of land use, and merge those together. You also need to sort of buffer the land use so that you can fill any holes. But there are problems about that because there are certain things like you get industrial areas which are in the countryside, and at least in my part of England, you get lots of parks in rural areas. Nottinghamshire was full of very rich dukes who built vast estates with parks in. And the whole area is called the Dukery, and they're about these vast parks. But they're probably not what people conceptually think of a park in OpenStreetMap. Our park concept is very rooted as an urban park. There are other points you can do. I could have tried POI clustering, conflation and multipliers. These urban areas can be potentially useful. If you know Richard Fairhurst's cycle.travel, he still lacks a good European data set of urban areas to enable the kind of routing he does. Another area which is fun is hydrographic basins. And I think most people will know Amanda's waterway map here, which she builds with by chaining watercourses together. At various times, I've done that the same for Great Britain, here below with using DB scan clustering. And this shows the English Lake District, where I've tried to fit holes round the individual groups of waterways. I haven't included the lakes there. And the idea of these holes is to actually find the watersheds, which would be interesting if you're interested in any kind of hydrological modelling. If it rains, as it has been in southern England, where's the rain going to come out? Lakes provide a particular problem in that you could simply just take the outline of the lake and treat it as part of the graph, but that doesn't give you flows. So you want to find the center line of the lake and connect it to all the inflow streams. You can do this. There's something called skeletonization, but it doesn't produce the right results. It has lots of dangling bits which don't necessarily go, and it doesn't necessarily give you a good center line. So finding center lines turns out to be quite a tricky problem and useful for all sorts of things. And here's my last example. Strangely enough, I've got Robert's Dundee High Street. I also tried to build 1D maps, as I call them. But I chose roads with lots of little bits of dual carriageway, slip roads, etc. And my approach was to buffer the road geometries and then try and find a single route through that, which I then called my linear way, and then did similar mathematical transforms to those that Robert described. So that's a really rushed through a whole range of techniques to try and derive additional data from OpenStreetMap. What you'll see is there's a commonality of different techniques. We want to find all the disjunct graphs, chain ways together. We need to think about finding midlines of various objects, lakes, road buffers. DB scan clustering offers a plethora of different ways to solve many of these problems. We also need to do lots and lots of manipulation of polygons, not just buffering holes. And one thing, you may want to transform that data so it looks like existing OSM data, so we can use the two data sets together. There are a number of things I would recommend. Use divide and conquer approaches. Don't try and solve the problem all at once. So you can segment the data. If you've got complicated things, you can often turn it into a non-geospatial thing and put the geometries back at the end of your processing. You often need local contextual parameterization. You can't use the same values for concave holes everywhere. You've got to do something a bit like what Robert described with trying three different parameters and then choosing the one that fits. You've got to be defensive. There are lots of bugs, lots of holes. Polygons get broken, they get fragmented into little shards. And if you're not putting, a lot of the time you can't put this data back into OpenStreetMap. So there's a question about where to put it. And I've tried with GitHub, but I found it profoundly unsatisfactory and I haven't found anywhere else to put it. So I'll just leave you with 3 challenges. Can you interpolate addresses from a very restricted number of addresses along a road? For instance, if you've got the shops with their addresses mapped, can you predict all the other house numbers? One thing I have, which came up yesterday, was we don't often have a low water level line, and there are a lot of applications which could do with that. But you can buffer island, but if you want the low level line assigned to Antrim, then you have complex bits where the buffering of different counties overlaps, and I haven't solved that. And I put sidewalks from sidewalk star tag, but actually we heard Dustin Carlino tell us how to do that yesterday. So I hope that gives a flavour for some ways to approach finding data which is in OSM, but not explicitly there. Thank you very much.
Excellent, thanks a lot. Do we have any questions?
Not exactly a question, but just 2 more examples that fit in this theme of like procedural generation, filling in gaps in the data. One is if you're trying to estimate the capacity in a parking lot, and you have the parking aisles mapped, which are like the bits of service road that you can draw down, then you can, if you sort of know vehicle dimensions, you can just fit a bunch of rectangles against those until they stop fitting. And this is like a reasonable heuristic for it. And then the second is the OSM Berlin group a bunch of years ago made this absolutely incredible map to count the total number of parking spaces, like street parking spaces in the city. And at first they were considering like splitting a residential road a bunch of times to kind of capture, like where parking bays appear and disappear. But then they realized actually people are already mapping driveways, and there's like regulation about within 2 or 3 meters of the driveway you can't park a car. And with those methods, they were able to like get incredible results without having to do that much effort. So. Oh,
thank you very much. It's very nice to hear other examples. I'm sure there are lots and lots of them.
Do you want the question repeated for the recording?
Yeah. 2 additional examples were provided related to, one, calculating parking capacity in parking lots which only have the parking service aisles mapped. You can just fill them with a rectangle which is of roughly the size of what you expect a single parking space be, and then that gives you an estimate of capacity. And the second example was the Neukölln project in Berlin, which provides fantastic cartography of street level detail. And there, instead of having to chop the street up into lots of individual segments to map that there were 3 parking spaces on the left side and 4 on the right, they could just do that by a knowledge of the local regulations applied to the whole road length, and then they could calculate the number of the available length of the road for parking as a fraction of the total, and then generate sensible numbers and sensible visualizations for that point.
Any more questions? Okay, well, let's thank Jerry again.
Thank you.